As you will see, I had a lot of topics. And fortunately, though, each one will only take 20 minutes. So, you guys are all safe. The first topic's easy because my longtime friend and colleague Dan Arvizu is here, and he'll take care of that one. So I thought I'd spend a little time on the new U.S. program, which very few people understand. And actually, this program is headed by Christiana Hansberg, who many of you know. And that's why there's no U in KEST. And that's how it's pronounced. This is a big program. Actually, this is one of National Science Foundation in the U.S. is one of their most prestigious programs. And when she came back, she came from the University of New South Wales back to the United States. One of her goals was to win that. And actually, we wrote the first proposal together. On August 17th, it was announced that she did win it. And I'm going to count on the fact that you folks can read. I cut this down to 70 slides, so I'm going to put your seatbelts on. It is a big program, and the $18.5 million the first 5 years from the National Science Foundation is scheduled to be 30% of the money. So basically, it's up to them to raise the other 70%. I think it's half matched by their university, which by U.S. standards, matching at a university is unusual. Basically, it's a very ambitious program. So I'm going to fly through these slides, and I'm going to be around. Actually, I'm going to be around for about 3 years. So you can ask me questions about it. It basically, the National Science Foundation program, this particular one, is just a huge, broad program. And they are known as the hardest programs in the U.S. to manage. Since Christiana is a longtime friend and colleague, she's fully challenged. But we're part of the program. And we've long been part of the program at the University of New South Wales. And you're going to see as I fly through what the program objectives are, that our program in the School of Photovoltaic and Renewable Energy Engineering actually does most of what this program is setting out to do. And some of the goals of this program, we actually already do. So we're going to be a lot of help. The quote from Lynn Preston. Lynn Preston is the official at the National Science Foundation. I should point out that Dan is on their board, so he's going to get to know Lynn. Lynn has a real vision about engineering research and engineering education. And at the first meeting between Lynn and Christiana, which I and others were there, it was kind of the basic presentation, and they were sitting there paying a little bit of attention. And then somebody said, well, what about the educational aspects? And for those of you who don't know Christiana, that's when she really lit up. And that's when the people at NSF lit up. And they really wanted her to win. And even more important, they want this program to be a success. But there is, as there is in most important programs, a single individual who started it, and that'd be Lynn Preston. This is what the program is setting out to do. I think it's inhuman what they're trying to, all the things they're trying to accomplish. But, and you know, only Christiana would trace everything back to quantum mechanics. So if you can't trace it back to quantum mechanics, it's probably not a real device. She kind of re-quoted Thomas Friedman, which is one of the many things that she understands. And it is about the terawatt challenge. And in fact, embedded in the program and embedded in their mission is the route to widespread use of photovoltaics is efficiency. So, and I know that Jim Torpy will agree, because this whole company is built on that. But in simple terms, if you think about the natural markets for photovoltaics, they are rooftops. And because you're on the customer side of the meter and the rooftops are already there, there are studies that show that you can get all the incremental energy, electricity you need for a city like Seoul, Korea by using existing rooftops. An important policy study. All right, well, you got to really love charts to begin to love some of these things. This particular chart shows what they're, actually, I'm sure it's obvious to everybody. This shows how you integrate all the technologies. This will be on my first quiz, by the way. So, but anybody caught understanding it is going to have to tell me why. Now, this is a famous chart. This chart is Lynn Preston's invention. The whole NSF ERC is based on what are called three-level diagrams. So at our first presentation, we actually modified this into something that we thought was plain English, to which Lynn said, gee, that's really an interesting modification of the three-plane chart, which I thought meant don't put it in your proposal. So at the end of it, I said, could I hear that again? She said, yeah, it meant don't put it in your proposal. Put this in your proposal. So we did. And actually, it is her vision. And her vision of engineering and what engineering can do is one we can all aspire to. And she runs one great program. But in case that you were worried that there wasn't enough to do, it's a K through 12 program too. And it really engages a lot of people. Dan's looking at this and saying, for $18 million you get all this? Actually, it's more money than that, but you do get all that. And I mean, they know when they're doing this that basically it's a high risk, high reward program. So they really do know it. Actually, I'm very pleased to say they absolutely know what they're doing. And then everybody knows how to get from discovery to commercialization, right? All the steps in between are all the hard work, which all of us do. And actually, as you know, this school does it extremely well. Probably in photovoltaics better than any university in the world. And so the goals of this program absolutely match what we're doing. Not surprisingly, much of her learning about how to do this came when she was on the faculty here. Now, that's kind of the new US program. It's clear to me that we fit. I'm not sure if it's clear to everybody else because I just did a $50 million proposal in 20 slides. So for those who don't know about our program, and that would be Dan and Jim, and that may be all. And so nobody thinks that I understand our program. These are Richard's slides. So, and that should be obvious from the first slide. Actually, I've already told Dan. Actually, we have 52,563 students, as I recall. So it's bigger than that. It's an incredibly compact campus. I went to the University of Illinois, which had at the time, well, it has actually more students now, but it has a much bigger campus. And even the University of Delaware, with 16,000 students, has a much bigger campus than you guys have here. So you really pack it into a really impressively compact footprint. Yes, and so do your laboratories. I mean, I had to take Dan to the Spree laboratories today. Nobody would believe that the world's most efficient solar cell was made in those furnaces. In fact, we stopped to get a picture so that we can show everybody. One of the many times I visited was '05, and I actually relaid out my lab and canceled my furnace order to bring in mini brutes, because they are really workhorses and they work all the time. And we've had very good luck with them, which is good luck because you guys have had good results. This is a really big program. This program is one of the best kept secrets in photovoltaics. I'm so pleased that Dan is here to learn more about it, but I came, actually people know why I came. I came because I was invited. I also thought this was the best place for me to finish some important research that I was doing that I could not do, I didn't have the technology or the capacity to do at the University of Delaware. But And actually, people walked me by the Tyree building and the TETB, but I had no idea what it was. They didn't show it to me until I arrived in October. It's spectacular. So you guys have something special. So I came because this is the best program in the world, and I was invited, but actually it's better than that. And I'm hoping to add some value. We'll know in 3 years, I guess, maybe sooner. I'm not sure how patient you guys are. According to my slides, this is not my next slide, but that's okay. And that one's not either, but we're going to catch up. I think I skipped a couple, but well, and for those who don't, there's a lot of students here, and there's a lot of PhD students. And I typically carried 12 PhD students, so and I had probably the second biggest program. And Christiane and I together carried about 20. You guys have seen this slide before, and I don't think you can do a talk here without showing this slide, so I don't have to explain it. I'm going to fly through your research because I promised some people I'd spend a few minutes on my own research, and I'm kind of on schedule. So you all know about what you guys call first generation. There's a lot of really neat technology that most of you do. Inkjet printing, I picked that out as one of the ones that is really a game changer, and probably the game will be changed here. Actually, I reviewed the first paper on this product, and I said that this is a really interesting product. This is a really interesting invention. It ought to be published because it's interesting and it's novel, and it'll never achieve a decent voltage. It probably won't go over half a volt. And for those who know me well, that kind of is a showstopper. I actually reviewed the next 4 papers too, at which the folks here sent the word back to me through Christiana, tell Helen to quit talking about voltage we know. So actually, I think then you put me on the no review list. But I always approve the papers. I said, yeah, but you can't talk about, you're not going to do 20% at half a volt. And everybody knows that. Some of us believe that the next solar cell beyond crystalline silicon might be a silicon tandem. And there are a number of ways to get there. Much to my surprise, Martin also thought that, and it was also in the ASI recent solicitation. So, and if there's a beyond silicon, it's a silicon-based tandem. So I'll stop at that point on that topic, and happy to develop it further later. Obviously, I'm a fan of spectrum splitting, and you'll momentarily find out why I'm such a fan of spectrum splitting. And finally, photoluminescent imaging. I first heard this work at a workshop. I went up to Torsten afterwards. I said, this is really important work, and felt strongly that it should be given its recognition, which it has been. He actually tried to commercialize it at the wrong time because the bureaucracy got in the way. And as happens in many projects, people were so busy cutting up the baby and without deciding to actually grow the baby into an adult that the project took a while to get started. But this is backwards. This is really great work. Actually, I try to do this with LEDs. I don't like to put serious lasers in my laboratories because they're open access laboratories. And the student could never actually get close. So when I came here to visit in February, I went to Torsten, I said, can you do it with LEDs? At which point he took me to the machine that was doing it with LEDs. And I said, well, you obviously calibrate them at the current densities at the maximum operating point. He said, yes. That student, fortunately, is happily working for somebody else right now. And students self-select. So that really worked well for me. All right, so what do? That's all summarized in one slide. I could blame Christiane on this slide, but I won't. It's actually mine. And I'm going to try to explain a little bit about what I do, and which will give you a hint about what I'm going to do. And if it's unclear, it's probably because it's always unclear. I'm much better, some of you already know, at asking questions than answering questions. And if you study under me, and wonder when I'm going to answer a question, you'll find out the answer is never. But I'll ask questions that'll get you to answer the questions. And if you're comfortable with that, that's going to work well. My first year students always tell I'll go to my older students and say, will they ever answer a question? Now, here's the good news. Leela, pay attention. The answer for the first 6 months is always, actually, Stuart gets this right every time. Who knows? Matt, you know. What's the answer for the first 6 months? What's the most important characteristic in a new solar cell? Single characteristic, one word. All right, who said it? Somebody said it. It's, what is it? It's voltage. It's always voltage. If you can't get the voltage, don't bother. When I came here for the interview in February, all you guys were talking about achieving 740 millivolts. I can't get over 660. There's nothing I can do to get over 660, of course, except turn the light up, and that doesn't count. But it's all about voltage. You get the voltage right, you can do everything else. Don't get the voltage right, there's really no hope. And you guys do the voltage. So I'm going to kind of summarize. This is basically everything I do is based on rigorous quantitative predictive models. I'm all about predicting the results of my experiment. And I do that, or not, actually, I'm all about you predicting the results of your experiment. How many times, what fraction of time do you think you get the result that you're expecting with a new experiment? What fraction of the time do you think you get it? Somebody. How many people think you get it half the time or more? How many people are awake? Half the time or more. Emily, did you say half the time or more? Or you said you're awake. Okay. That's right. You are, obviously. How many people think it's 10% of the time or more? It's actually not that bad, but it's happened to me. I think I've had a new experiment work about 4 times, but I run a new experiment several times a week. And that's the whole point of the predictive model. It's when you don't get what you expect that leads you to analytically go to the next level, as opposed to try this, try that. In fact, that approach of try this, try that, which I actually define as plunk and dunk, is not my favorite approach. I want to know why we're doing what we're doing. It's just much easier to spend time understanding and analyzing the experiment before we run the experiment. Experiments are hard to run, and it's even harder to run them right. And you learn 2 things when you don't get the right result. Usually it's because the experiment you ran wasn't what you expected it to be, and there were other variables that you didn't know. In solar cells, everything interacts, so it's really, we got a lot of problems there. So these are all the topics I work on, and that's the approach I take, which should be summarized, which is summarized. Actually, I understand why I'm an engineer. So, and this is one of the classic definitions of engineering. I tell students, and I used to teach the sophomore class, I used to teach big classes too. There were like 95 students. You guys would think that was a small class, but, and I would tell them that, you know, if you're an engineer and you're a good engineer, you get to pick the problem. And that is the classic definition of engineering. That's why many of us are in the field. That's why many of us are doing photovoltaics. We think photovoltaics is a good solution. We think we're bringing energy to the people as opposed to trying to bring people to the big central generation plant. So if you're a good engineer, you get to pick the problem. I picked this problem. We have basically a microsystems approach. I really think we're doing microelectronics, so we do everything with photolithography. And we build some really interesting structures. We can't build super high performance structures. Having said that, we did set a couple of efficiency records. Actually, setting efficiency records, I always thought that was kind of, I'm sorry guys, I never thought that was a worthwhile goal. I just thought that was a result of doing things worthwhile. And Christiane always argued with me that, you know, that's not right. You know, people really pay inordinate attention to high efficiencies, and they do. So she was right about that. So every time we'd hit a new number, you know, we'd get overwhelmed with attention. And so, although I still think it's the result, it is important. And if you want to do ultra high efficiency, you got to do multiple junctions. You shouldn't do really more than 3. This chart almost explains. But if you want to do that, and you want to do that, and you want to look at new materials, there's only one thing we're looking for in a new material, right? We can select new materials really quickly from a list of all of it. And what's the one thing we're going to look for? Let's see, is it going to be that it's inexpensive? No, Matt, you get it this time. All right. It's going to be, whoop. It's going to be voltage. It's always going to be voltage. And the fact that we understood this led to us winning, actually, a substantial contract. So you can do everything. You can engineer pretty much everything else. By the way, we ran a very large program, and we did find some exotic material systems that could do voltage only. So, which fortunately, somebody decided to stop funding that before we found out why. It was only voltage. So we did win a big program. So, and in fact, this at the time, this is probably the biggest program there's ever been. It actually grew to a $100 million program. So before I came here, I had some experience with big programs. So this program was scheduled to be 4 years, and we're now in year 7, but we're going to wrap it up. And in fact, the review meeting is in 2 weeks, and I'll do it from here. It's a big group. It was a wonderful program, absolutely wonderful program. I got 12 PhDs out of it, and we probably ended up with 40 PhDs. You know, it's really interesting. Go to the DARPA review meetings, and you get the generals, because DARPA is the Defense Advanced Research Projects Agency, so it's a very high visibility organization. And the generals say we need more educated people. We don't have enough educated, they say trained, but it's really educated. They don't know the difference. But they won't fund them. They want to fund results. So I made a deal that there were solar cells that they needed for this program that actually only I was willing to make. They were too small and too specialized for any company. I actually tried a bunch of different people to get to make them, including you folks. And so I would make those solar cells for them if they would support 8 of my PhD students. And that deal and they've all graduated, by the way. And that, in fact, 7 graduated this year. So that, they held to that deal. And that's kind of a, Dan, you gotta be pleased that our government really actually did that. And I'm not sure how many people knew that was the deal. And when they wouldn't give me all the money I wanted, they would only give me $1 million a year. I said, well, that's okay, then I won't make the solar cells. They said, actually, Alan, the one thing you will do is make the solar cells, and then you can do anything else you want. So, but it was a good deal. But this great program. One, we separately integrated the optics and the device. And that was a lot of fun, and that's opening a whole bunch of avenues. I know you folks already do that. But the best part is we were asked to invent, develop, and then transfer to production. But we also knew that we needed a bunch of junctions. We needed more than 3 to get over 50%. And we immediately realized that if you did them all in optical series and electrical series, that wouldn't work. It was too constraining. So we did the lateral conceptual design. It was a big team. So you know, how do you manage a big team? Well, you don't micromanage it for sure. What we did was we divided it into 3 parts. Since the program manager at DARPA was an optics expert, I separated that out and gave it to him. I gave the research, which is lower right-hand corner, to Christiana, and she did that well. And since we were really only going to be measured by solar cell efficiency, and the whole point of a big DARPA program is phase 1 is a year. It's not well known, but only half get to phase 2. Only half get beyond the first year. So, and so everything was about the efficiency. And let's see if that number shows up. This was a big program. In fact, it is described as a, one of the times the University of Delaware was a little piqued with me, and they told DuPont that I keep bringing in big complex programs and they don't understand them, to which DuPont, a very senior executive, said, then you prefer small, simple programs. But I do like big complex programs, and this is and was a very big program. And this actually comes from our original proposal. Tells how to get over 50% as a sum of solar cell efficiency. This actually tells how to reduce the cost. And that was our sum of the solar cells result, which has a lot of interesting stories all by itself, but a very interesting result. Never went into the record books because there is no such thing as sum of the solar cells. Solar cells, by definition, have 2 terminals. But Keith Emery said modules actually don't. Modules don't have a specified number of terminals. So once you make the module, we can put that in the book. Actually, and as Dan knows, and anybody who's worked with Keith Emery knows, he's just a fantastic guy to work with. And so we were together trying to figure out what are the rules for putting a module in the record book. And we're sitting together, and he said, well, I guess we get to make the rules. So, and of course, he got to make the rules, but I got to participate. It was a lot of fun. So this is what we did. That's what we achieved. Previous to that 38.5, the highest achievement was 36.7. That was also ours. And previous to that, the highest achievement was 32.9. And you know, in spite of my objection that efficiency is not the only important thing, maybe it is. Oh, and this gifted student actually also led this. She led the systems work and she led this work. Her name is Xiaoting Wang. You'll see a picture of her shortly. And I told her, send me your 5 best slides. So she sent me animations. So there's really 20 slides in her 5 best slides. But nobody would ever call Xiaoting stupid. And that's actually a picture of it. I love to explain the details of that picture. That picture is full of content. And I'm going to have to spare you today because you only gave me 30 minutes and I've already used them. Not quite. She actually did measure 39.5% efficiency, and for various reasons, smaller numbers were reported. It's all okay. When this came out, actually the official measurement was 36.7. After all the work and all the discussion about exactly how do you measure it and what's the right thing, somebody, when they transmitted it to the journal, couldn't read their notes. And a 7 became a 0.1. So it came in as 36.1. The paper says 36.7. And it says that's the NREL measurement, but the journal says 36.1. And so when I got this, I was rather pleased by this. I was rather pleased by what it says. So I sent it to my students, and Xiaoting calls me up. She says, she sends me an email, but it's the wrong number. I said, Xiaoting, how many graduate students are the lead author on a paper that cites a record efficiency? And this work was all student-led. She's kind of gets over it a little bit, but she still says it's 36.7. Actually, it was really 39.5, but that's a different story. Shifting a little bit to other research that I do. I've been doing thin silicon research. I've been trying to make a thin silicon solar cell work for, I actually filed my first patent application in 1980. Zhang Rongxi says that his first research was reading my papers, which was kind of him to say because he was in my presence. But I've never figured out how to do it, but I think I got it now. And I think I can finish it here. So I am going to do that, and some of you folks are going to help me. The one thing I bring is I bring a technology that does silicon layers that are 5 to 10 microns thick and have 50 microsecond lifetimes. So, and for all of you guys who are quickly calculating, that should be 740 millivolts, right? And you guys know how to do 740 millivolts. Of course, we got to passivate both sides. My technology allows you to do that independently. So we can passivate both sides. So this is an important project. Stuart has embraced it, and as I expected he would. And it was one of the things I came here to do and to finish. And we can do this here, and it'll be important. And somebody will say efficiency is more important, but okay. But it's 5 to 10 microns thick. And if you make it 5 to 10 microns thick, and you light trap it, and you passivate the surfaces, what'll happen? What parameter will get better? All right. Voltage. Of course, it's all about voltage. So, and all we need is 740 millivolts to get to 23%. So this can be an important solar cell. And we understand it, and most of the people in this room understand it. I'm going to give Haley the test later on, but the rest of you are kind of on. This is the group. I actually, you may notice, some of you do, some of the best work in very thin silicon solar cells, and Emily's one of the researchers who does it, is done by women. The lead authors are women. There was a conference in Hamburg, and there was a session, an oral session on this. All the speakers were women, and I think actually this technology is so complex, and it also takes intelligence, it takes great lab skills, it pays attention to detail, it takes dexterity. I'm thinking maybe only women know how to do this. I know how to think about it, but they know how to do it. So it was a remarkable coincidence. And I actually said something at the time which Emily probably remembers. And you don't need the light trapping to get the voltage. So you do the light trapping later on. That's just optics. And I don't want to say that optics is simple, but compared to photovoltaics, optics is simple. My watch says I got about 3 minutes, maybe 4. I also do 3.5s, and the folks here thought maybe I should figure out how to grow the 3.5s on silicon, because that might make an interesting tandem solar cell. That's Ken Schmieder. He will arrive here as a student on January 15th, and maybe to visit later this month. And we are doing gallium arsenide phosphide on silicon. And this is the beyond silicon solar cell, if there is a beyond silicon solar cell. And it's a very interesting solar cell. And we'll be bringing this technology here. That's my spectral splitting group. That is Xiaoting on the left. We actually caught her in a picture. Basically, the research that she did and the research she did on record efficiency was definitely worth a PhD. But she had a lot of capacity, so we decided to work together to see where this capacity would take her. That meant a lot of ability to do more than just make a record-breaking module. And so we began a study of what's the value of efficiency, because maybe we're wrong. Maybe efficiency doesn't have any value. Maybe you should just make 5% or 2% solar cells and paint them on. So we have a major study on the value of efficiency. For those who really studied it, and the folks from SunPower certainly have, it's based on the capital cost. You can do everything based on the capital cost. And we did levelized cost of energy. We used the solar advisor model from the Department of Energy because it's transparent and available. And we actually looked at the flat plate with and without tracking. This is a do 5 slides. This is an animation. This is 1 slide, by the way, guys. So they're a very clever woman, so I just couldn't take them all out. And we basically looked at what can you do with concentration? What's a 500x concentrator do? And we actually realized that the module needs to be over 30% to be useful. And concentrator people rarely measure the module. In fact, they almost never measure energy. I don't know how much of that you guys are funding, and if I've gored a couple of oxes, I do that all the time. Then we decided how important is current matching, because part of the lateral spectral splitting is we don't need current matching. And everybody will tell you that under clear sky conditions, that current matching doesn't really matter. There's, the currents are matched, and the times they're not matched aren't really significant. So we began to collect the real data, and there are very few real data sets. And when we collected the real data, let me see how far she took this. Oh yeah. You find that basically, instead of getting the clear sky energy, which is shown in the top curve, let's do. ST is separate terminals, and 2T is 2 terminals. So under clear sky conditions on the right, under high DNI, it doesn't matter. But on the rest of the time, it does matter. And if you calculate energy, it really matters. And actually, Xiaoting was at NREL a couple of weeks ago, and they suggested she use a different database, which would give her a different answer. And she actually, we're just about to submit the paper for publication, for review. She said, what do you think we ought to do? I think we should do both. And if in fact they're right, and it gives a different answer, like using this different database, then we just say it's important in which database. So she was pretty sure, as were the folks who were advising her, that if you used a different database, the loss would only be 4%, it'd be insignificant. By the smile on my face, you probably think the loss was greater than 4%. It's 20%. And this will be one really good paper, and I hope somebody in this room gets to review it, Because if you are a triple junction guy, you'll slam it. And that happens all the time in this field. So, but this paper is unassailable from its content. And this very talented woman did the work. So, she just can't stop. So we got a loss analysis. She did a detailed loss analysis. I'm going to spare you because I'm eventually going to leave. We also did a lot of energy production work. That is Francisco Gil in the middle. He's a teacher at a university in northern Spain. And based on this work, which he did under my supervision on 2 extended stays at the University of Delaware, he actually completed his PhD last Thursday with highest honors from the University of Burgos in northern Spain. And I was basically, we did it by video. I kind of asked them, well, how do you usually do it by video? And they said, we've never done it before. But that was a lot better than going to Spain. Finally, what is this program all about? How do we do collaboration? So this actually comes from a public document that you guys sent out. And I said, rather than put the answer down, I just repeat the document. The big US programs have shared objectives with our program. We're probably have more PhD students here than the US program combined. So there's a lot of opportunity. One of the features of the US program's proposal was the opportunity to work on a pilot line, which is actually a very small laboratory line in about 100 square meters of space. Obviously, we have the SURF, and that would be a really good learning opportunity. And finally, in summary, it's all about the folks, the students. That's my student group in the fall of 2009. That's the group at graduation this summer. They're actually 6 of them got PhDs, and I didn't sleep for 2 months, but they all got their PhDs. 3 of the others got master's degrees. 1 of the others is going to get a PhD. 4 of these students are going to be here. And Xiaoting's in the center. The pup is really a lot of fun, but he doesn't do well on the exams. And I want to thank everybody for their time and attention. And and kind of what are we doing it for? We're doing it for those babies. So, thank you.